Very good morning to all of you. Welcome to this third day of this ICT-based course on embedded system practices. Today we have with us our expert, Mr. Sandeep Singhai, who is a senior scientist in Central Scientific Instruments Organization. And today's lecture, he is going to discuss the industrial applications of embedded systems, wherein he will be discussing the development of head-up display. It's a very ambitious project of CSIO, in which the head-up display he'll be explaining to you. And I hope you'll have a rich experience. Thank you, sir.
Thank you. Good morning, everybody.
ऑडियो थोड़ी कम जाती है
कोई नहीं बस just the control of my resources. So, good morning. I'm Sandeep Singhai. I'm from CSIO, and basically, I've been working in this project for around 10 years. Defense projects are mostly long gestation projects. So, we have developed one system called head-up display for the first indigenous aircraft of our country, Tejas. You might have heard about light combat aircraft LJ Tejas. That is fitted with the device we have made. So we are fifth in the world who has this technology, and prior to this there were only a few countries which used to have this technology. And so with our work, we have actually reduced the price of the device for our country by half. What it used to be charged for prior to our development was double of, although we are not right now able to replace it in all aircrafts, but still in each and every development project which has some indigenous development part, we are always considered for head-up display part. Whatever aircraft, whatever program, whatever comes in, either it be Sukhoi or whatever, whenever development issues comes up for indigenization, we are looked for as far as head-up display is concerned. So today we will briefly discuss about the development of head-up display. And since the mandate of this talk is basically embedded systems more or less, so being a more informative lecture, I will also add some part of embedded systems to the limit I can divulge. So because it's a strategic project, so I will discuss something, some small parts which have some software hardware interaction in the head-up display, and I believe that it will be an interesting talk. So basically, the outline of my talk is I think all centers are also well connected and they are able to hear me. It is always good to have some live participants also, because it helps in making some eye contact, and it makes you be expressive. Otherwise, you don't know what are the emotions of who are sitting on other side of the table. So today I will talk about development of head-up display for strategic applications. How we go around, basically what is the process and why it is so lengthy. At times people think that it goes on. So why it takes time. Then basically, before going on to what is HUD actually about, I will put some light on why HUD is needed altogether in an aircraft. Mostly in fighters, it is a standard equipment till date. Then we will discuss about the composition, challenges and features of head-up display, followed by some embedded parts in the head-up display which I personally have worked upon. One is called the built-in test equipment, which is basically the health monitor of the entire device. Because in the philosophy of any avionic development, the basic core is that if your device malfunctions, it should shut down rather than causing any distress to any other thing. So whatever there is in the cockpit, they are basically called LRUs, line replaceable unit. Means if you replace that particular unit, The only effect will be the functionality which it was providing. Otherwise, it will not affect any other thing in the aircraft. That is the basic philosophy of any cockpit device, that it should not disturb the functioning of other devices. Until unless power is coming up, there are around 256 LRUs in a particular cockpit, more than that in some, but each LRU is independent of others. It doesn't disturb the functionality of others. Okay. And correspondingly, the requirements are also like that only. For example, EMI EMC problems are there with any electronic system. So electromagnetic interference and electromagnetic compatibility. Now, if there are around 250 devices in a cockpit, your device should be so that it should accommodate, it should be compatible to the total EMI generated, permissible EMI generated by all those 250. Plus, the EMI which is generated by your device should be less than the amount fixed for an individual unit. So in our case, we follow certain military standards for certification, testing, and then only we go ahead with our development process. Those are called MIL standard 461, 462. There are environmental standards 8110. So we follow all those, and then only we can have something which is airworthy. Airworthy means which can fly or which can go into the aircraft. Then, if time permits, we will discuss HUD's utility in other sectors. HUD is also seen as a potential use in many other automobile sectors, like high-end luxury cars. They are coming in some high-end luxury cars, but seeing the cost-benefit analysis, because our HUD cost around 60 to 70 lakhs. That can't go in a 3 lakh rupees car. So if we develop something for automobiles, that is a very cost sensitive product, not more than 5 to 10,000. They are coming in certain BMWs and all those, but right now it is not a standard product. As far as railways are concerned, railways vision is a big problem in different conditions of climate. Therein the concepts like synthetic vision are coming in. Synthetic vision is nothing but I capture an imagery or photo when something is clear, and then I superimpose it when it is hazy. But in case of aircrafts, it is quite a lot easier because you have limited airstrips. But in case of railway, if you develop some systems, they will be quite data intensive and there are issues. So for that, but still we have not got anything as far as project is concerned. We are primarily into the fighter aircrafts only. Now the first is, if you want to develop something for the avionics sector, or for instance for defense sector, what are the various elements which are involved in the picture? So the first element is obviously the funding agency, which gives you the funds for the development of any particular thing. As far as the first indigenous aircraft, basically the agencies which are involved at the white box level, there is one. It is again a specialized agency of DRDO called CEMILEC, which is situated in Bangalore, Center for Military Airworthiness and Certification. So anything which can go into the aircraft has to be certified for airworthiness by the CEMILEC or one of its 7 regional centers. So one is in Chandigarh called RCMA, Regional Center for Military Airworthiness, which is situated in 3BRD Air Force Station, Chandigarh. So we basically deal with RCMA Chandigarh for white box level involvement. All the designs, all the integrations, all the testing are witnessed and certified by those people. Secondly, once on the later stage, you have quality inspectors. They basically certify your product at the black box level. Means they are involved with the device performance at the input and output level. They are not concerned with what is going inside, but what they see is what you have claimed as input is being catered to you, as well as what is the output expected from your device without any disturbance. Since it's a display device, so it should not be without any noises, any disturbances, any ghost effects. Being an optical device, no parallelism and all those things. So, and then optical performance and everything, they are tested by the DGAQA person. So for that, the agency is DGAQA, Director General Aeronautical Quality Assurance. They are the quality engineers for any development work within the aeronautical domain. Now, as I told you that any product which goes into the aviation needs to be tested for environmental considerations as well as the EMI/EMC considerations. So since in our country there are very limited facilities for those things also, so various tests which we go into for a single unit has an endless list, starting from mechanical shock to thermal shock. Thermal shock is something we place the device into -50-60 degree environment and then suddenly put it into -55 degree environment. It should be operational in between. So the temperature range between which it should operate is +65 to -125, because your aircraft can stand in Suratgarh on a full sunny day as well as in Ladakh on a full snowy day. So those conditions, temperature considerations are there. Then you have solar radiation issues. Then you have humidity and dust issues. Then you have to test for rapid decompression sort of thing, means pressure varies because an aircraft can come down very fastly. So that change of altitude is very swift. And I have seen those facilities there is one Air Force facility in Bangalore. So they basically perform the altitude variation test on soldiers, because they test their adaptability to high altitude things and all those things, and that particular device they allow us to use for this head-up display cycle thing. So we vary the pressure from 50,000 feet height to 5,000 feet height in very short time. So those all tests we need to pass, and that is a very long journey. Basically, if one test is failed, then again you have to do lot of things, and then again you have to manage all those people, and then you have to go through it. So it's basically very, as far as my personal experience says, that this was the most time consuming part in HJT project, which we did for HAL. So these are various agencies, but we were fortunate that in each and every one of these parts we had people with same frequencies who were interested in indigenization, who were interested in having a national product. And then you have flight test engineers. You know, pilots are the most what to say, they have an attitude. They believe in love at first sight. Means if they don't like anything at first sight, they will, next time when you ask him how is it, he will not put an eye into it and just stand and say no, it is not okay. So there we also have those flight test facility center in Bangalore, NFTC it is called, National Flight Test Center, where all the test flights are undertaken. They are very specialized pilots of Indian Air Force who are on to deputation in that particular thing. So that is at the flight test level involvement. So this teamwork has basically paid us a lot, and a line replaceable unit costing around 60 to 70 lakhs. Then I think I missed one thing, is the production agency. So finally we are not able to produce it because we have only design facilities, limited manufacturing facilities and all those things. So in our case, we as a production partner, we have Bharat Electronics Limited, which is situated in Panchkula. The one very reason why BEL is suitable to us is that because of regional spillover. It is very near to us, and they have established all the facilities specifically for HUD, and it is one of an important avionic product which BEL Panchkula delivers. In fact, it is only now they have a big stream of avionic products which are supplying to LCA, but they also started with only head-up display. Because otherwise there is an understanding between these two public enterprises, BEL and HAL, that BEL will work only in the ground equipments and HAL will work in all the avionic equipment. They have an understanding. But in this case, somehow they reached into an extraordinary thing, and since BEL is basically solely producing head-up display for LCA. For other products, we are negotiating. Right now, we don't know whether BEL will produce or HAL Korba will produce, because HAL has a unit in Korba, UP, which is specialized for display systems or this type of thing. They have a lot of products which are either in TOT mode or indigenized productions. So we have developed indigenously, has gone into production as far as LCA is concerned, and is successfully flying in the Tejas aircraft. And then there is pipeline of other aircraft like HJT we have developed. It is in the final stages. Airworthiness has been cleared, and in some time, if the aircraft goes into production, we are hopeful that we will get this head also. Even in the newer programs of government like Sukhoi and all those things where there is a TOT mode concept, so we are being considered for that. Now, this was basically the actors in the entire scene. This is basically the process. So it starts with obviously proposal submission and deliberations. Then once the project is cleared, we go into a preliminary development work, and then a PDR meeting is held, which is called preliminary design review. And all those actors which I defined you, barring the production agency probably. However, in our case, production agency was always hand in hand with us. So all those actors, there is a PDR committee which reviews the design requirements, because what we get is we get certain performance requirements. What their agency gives us is certain performance requirements, certain environmental requirements, certain EMIMC requirements, plus an interface control document, a connector output through to which we have to design the head-up display. So at the PDR level, basically the initial design is deliberated, and then the next stage is, once that is done, we go for a critical design review at a later stage.
I have a query.
Yes.
There is electromagnetic spectrum of EMEI.
Okay.
In which range this is being lined? किस range पे line करता होगा? It's extremely low frequency level or mid frequency level?
No. There are various type of things in the electronics part of head-up display. Then there is movement of the 28 volt power supply. Now, since I will discuss in detail, since our system is a CRT based system, so you are aware that CRT requires very high voltages for in the range of 15,000 volt. So that current flows in. So there are various type of EMI. So we check it for each and every. We do RS01 to RS03. We do CS01 to CS03, as well as then susceptibility test of all entire spectrum, which is yes, entire spectrum, whichever is specified in MIL standard 461 for the purpose of any avionic equipment, we test it. And if there is leakage or any issue in anything, naturally there is emergence of EMI from various things, but we pack it in a manner that leakages are checked and things are kept into limit. The entire spectrum we check it, whatever is specified in 461. So once the critical design review is done, at the critical design review stage, more or less the design is freezed. So once this is done, we are more or less confident that we will be able to develop something which will be as far as avionics standard is concerned, it will be able to cater the needs. The next stage is form fit functional unit. So this is the first unit which we come up with. It is called form fit functional, means it is in the form in which it was required, it is fit for operation, and it is functional. It gives you the desired results. But at this stage, whether its endurance is not tested, neither from the point of view of environmental specifications nor from the point of view of EMIMC standards. Form fit functional is, it is working, it is taking the desired input and it is giving the desired output in the form it was required in the specifications. Now the real journey starts after this. The next unit which we come up is safety of flight unit. This is the unit onto which we do all the tests, all the specified environmental tests. There is a list of 25 tests, which includes, as I told you earlier, mechanical shock, thermal shock, humidity, temperature shock, rapid vibration, stress test. Then there are solar radiation tests, and so on. There is a long list of qualification test procedures, which we have a standard document for that purpose, based on those standards. So this SOF unit, once done, that ensures the things which have been satisfied at the FFF unit level are also in conformance with the environmental and the EMIMC requirements. So at this stage, we are sure that we are able to produce something which is airworthy. But this particular unit does not go into the aircraft because it is basically a burnt out unit. जितना भी testing होना था, rugged testing होना था, even we do rain test on it, we put into open water flow and run the unit. Humidity test is for 15 days, 95% humidity cycles for 15 days we perform. So this unit basically once cleared is basically archived, doesn't go into the aircraft. Now the next stage is to come up with Yavadi units. Yavadi units are those which goes into the aircraft. However, these are also tested, but not those stringent tests are not applied. We do ESS testing on this Yavadi units. And within ESS, it is basically thermal shock as well as some vibration testing for dry soldiers and all those type of things. So once this ESS testing is done, an Yavadi-ness certification is provided to us by RCMA. Once that is done, now that particular unit can be fitted into the aircraft. These Yavadi units go on to the design agency or funding agency. There they test it on the test rig, and once the test rig performances are okay, they install it in the test flights and do test flights for that. Test flights are also conducted routinely for various purposes. There are days when specifically a pilot checks the HUD, or he checks the radar, or he checks some other HUJ or whatever. So in our case also for LCA, this all was done. At JT, we are at this stage right now because the entire program is being delayed somehow. Then the next stage is limit LSP production. These Yavadi units goes into for limited series production, and then once everything is cleared, because a lot of mods come in and there are a lot of modification requirements come in, then we have to change those things. Again we do ESS, again we get certification, because obviously it is not foolproof anytime. So then finally, once everything is established, settled, it goes into series production, or we transfer the technology to any production agency. As in our case, we have done it to Bell. So they have given some upfront payment as well as royalty component in it. So then it goes into series production, and it is always in tandem with the aircraft of the status of the aircraft also. Because you may be aware that Tejas has gone into series production now. It's a very old project, but if I am talking lot of stories, this much story about a single LRU, you think in the entire aircraft there are thousands of LRUs. So even in that case, engine is still not indigenous. Engine is still from GE. They have set a target for 2019 to work with some indigenous engine which has been developed by DRDO called Kaveri, you might have heard. But still the engine is GE1 in the LCA. Rest all avionics, as composite material, lightweight things, all those things. A lot of agencies are involved. Around 50 agencies are involved in the entire development effort. However, ADA is the main coordinating agency, and in the future the entire aircraft will be any case manufactured by HAL only, because there are no other manufacturers in India right now. However, since the defense production policies are changing, we can assume that in the coming future a lot of new things will come. Now till now I talked a lot about head-up display. I don't know you got an idea what head-up displays actually is. So this picture tells us something. So what is a display basically? So a display is basically something which presents the status of a man-machine system in our terms. Any man-machine system where there is an interaction between human and machine, the display gives you information about that. It can be anything. It can be a MFD, multifunctional display. It can be horizontal side displays. It can be FDDs, and it can be head-up display. Now, what is the difference between these two? Basically, if I say that all these MSDs, HSDs, and FFDDs are head-down displays, so that will give you idea about what I mean by head-up display. These all other displays are basically head-down displays. Means if I have to see into these displays, I have to change my line of sight. I have to look somewhere else from the outside world, or which in our language we call ambient. So I have to change my line of sight from my ambient. And in that context, head-up display is something which allows you to see the ambient as well as the information superimposed onto it in a manner that it does not disturb you, in a manner that it does not overflood you with information, in a manner that it helps you in improving your situational awareness. Why situational awareness is very important? It is not very important when you are driving in a city on congested road, but it is very important when you are driving on a highway with 100 plus speeds. And in case of aircrafts, you are driving at either subsonic or sonic or supersonic speeds, more than 1000 kilometers per hour. So in those situations, head-up display is very useful, and especially in case of fighters, where split-second decision making is sought, HUDs are further useful. So now what is a head-up display? These are various pictures. These are our basically proprietary pictures. The one on the below is very flight test page display of CSIO HUD. This was the first image which was taken with CSIO HUD. It was obviously a FFF unit, and everyone was very much elated when this image came in, because it was the first time that something came out. Otherwise, it was not a very swift journey. It was a very difficult journey. This project was left by one DRDO lab prior. It was not given to CSIO as a first priority. First, it was given by ADA to some DRDO lab. When it refused, then it came to CSIO. So this image was a proof of our capability. The first one at the top is basically the head-up display for HJT 36 Sitara. It is basically a trainer aircraft which is being developed by HAL. It is under development right now. Test flights are going on. The second image is our HUD fitted into the cockpit of that particular aircraft. And third is the mock-up of that particular at some air show where the then defense minister, now president of India, Pranab Mukherjee, visited our stall. So it is basically, HUD is basically something which displays flight information in a collimated form. So that the pilot can view this information superimposed on his view of outside world. Now here collimation is important. Collimation is nothing but to make beams parallel. Or in simple terms, collimation is to focus an image at infinity. Now what is the benefit of it? Suppose if I put a hand before your eyes like in this manner, would you be able to see properly? You are disturbed. For example, you itself, you are disturbed. But if I put this hand somewhere near you, it won't disturb me. It will mingle into the entire scene. And I will be able to, if I want to, I will be able to focus on that hand as well as the entire scene. So the basic philosophy is that the head-up display symbology should not disturb your ambient thing, or it should not cause any tunneling. कि आप उसी में डूब गए and you forget the outside world. So with that ideology, we develop HUD in a manner that the image is focused at infinity, thereby ensuring that the pilot is able to see the ambient as well as with ease the superimposed imagery. It is an essential line replaceable unit of the combat aircraft which aids pilot for taking split-second decisions. Now, there are various scenarios in which a fighter aircraft will fly, will land, will fight. It is basically meant for combat. So their situational awareness is very critical. Now, if I can divulge into that environment, you think you are fighting with, you are a pilot and you are doing a dogfight with an animal fighter. So what all things you have to look upon? You have to look upon all the things of your vehicle. Fuel hai, ammunition hai, pressure level sahi hai, you are at a typical height, your radars are working, everything is okay. Number one. You have to communicate with the ground station for lot of things. You have to communicate with your friendly pilots. ऐसा तो नहीं कि आप अपनी country का जहाज उड़ा दो. Then you have to be aware about the enemy, that whether you are not logged into his radar, and then you have to attack. in this heavily loaded environment, you don't have much time or little time to look into the gauges which are below you, or radar or any gunpoint sensor. So in those situations, I will show you a video. HUD is very important. Now, as far as any aircraft is concerned, there are basically three movements of an aircraft vis-a-vis the three axes. The movement along the x-axis is called the roll. This movement is called the roll of the aircraft. Now there is this movement. This movement is called the pitch. And then this movement. This is called the yaw. Okay. So there are control fins for everything in the aircraft. If you see these ailerons, you might have seen when the aircraft, these happens like this. So they basically control your roll. Then you have this rudder. This basically at the back top fin, it basically controls the yaw. And then you have these elevators at the back fin. They basically control your pitch. Okay. So the HUD basically improves the situational awareness of the pilot, and how I will show you later. This is basically a typical navigation mode page of a head-up display. Now here what you can see is it visible? Yeah. Pardon?
Madam, a view is invisible.
Okay. No problem. It will be more clear, and basically the center with a circle you are seeing, na? That is basically the aircraft itself. And then you have indications for roll, pitch, and yaw. These are pitch lines at the top. You can see. Pointer हो? अच्छा नहीं अच्छा सेंटर ये लोग को तो आ जाता है ठीक है. Then you have this Mach number. Okay. So this Mach number is basically the speed. Mach speed is basically speed of sound. So if the speed is more than 1, it is supersonic. It is more than 5, it is hypersonic. If it is less than 1, it is subsonic. Then here this 3.9 is the acceleration. You have pressure readings, then flight path markers, altitude levels, all those informations which is critical to the pilot at any particular instance is displayed on various pages. Even this is one particular navigation page. You have lot of pages, there are around 16 pages in our HUD, wherein you can change the symbology which you want to see for a particular thing. And there are page shifters because necessities change. Sometime you may be into a gimbal lock type of situation, wherein you have lost your 1 degree of freedom. Usually you have a 3 degree of freedom. But there is one situation called gimbal lock, wherein two axes become parallel. Now your 1 degree of freedom is lost, then you need some decluttering modes for coming out of that situation. So in those things also HUD helps you. So now why HUD is required? Here we can understand the basic philosophy why actually HUD is required. Now HUD is important in these four things. Number one, flying and navigation. When you are flying, when you are navigating, HUD will give you information which is more precise, which is already available in other head-down displays. Basically, HUD gives you redundant information. It is already available in other head-down displays, but whatever is critical of those is available you pictorially so that you are more aware instantaneously. Then aiming and firing weapons, takeoff and landing. During takeoff, it's a very intensive process. Takeoff is a very intensive process, and as well as landing. And situations can be many. It can be a foggy situation, it can be a rainy situation, it can be a lot of other situations. And finally, there is one raster mode. Basically, HUD operates in cursive mode. Means it gives you symbology which represents the metric information which is coming from various sensors. Now, in case of night flying, there is one FLIR camera in the aircraft, forward looking infrared camera, which basically captures the thermal signatures. So those thermal signatures can be displayed. Raster mode is basically TV type of functionality. So that FLIR imagery is displayed onto the HUD screen. During nighttime flying is basically it is useful. Now, what is the utility of HUD during approach? I have shown one typical scenario. Now, there are three types of airstrips shown in this picture. One is the airstrip which is a flat airstrip, which is sufficiently wide as per standards. Now, in this case, you may be aware or may not be aware that whenever aircraft approaches the airstrip, it basically glides. It neither accelerates nor deaccelerates. It glides at a particular speed. Now, that glide path is basically based on the approximation of the pilot of the touch point, the first point he has to touch. Now, in these three pictures, you see three types of airstrips. First is a broad and flat airstrip. Second is a upsloping runway. And third is a downsloping runway. Now, in case of here with that blue line, they have displayed the ideal glide scope or ideal glide path on which the aircraft should glide so that it can comfortably reach the touch point. In case of a flat runway, there are or a sufficiently long runway having a good breadth runway, there are chances that the approximate glide path or the actual glide scope followed by the pilot will be superimposing on the ideal glide scope with the visual approximation. जो पायलट का विजुअल अप्रोक्सीमेशन हम दूर से देखेंगे यदि 2 किलोमीटर से, तो हमें बहुत आसानी से नहीं पता चलेगा कि ये ऐसी है कि ऐसी है कि ऐसी, हमें फ्लैट ही दिखेगी वो. तो उस हिसाब से हम जो मेंटल अप्रोक्सीमेशन पायलट करेगा वो सुपर इम्पोज करेगा इन केस ऑफ ए सफिशिएंटली वाइड एंड लॉन्ग और स्टैंडर्ड एयर स्ट्रिप व्हिच इज नॉट अपस्लोपिंग और डाउनस्लोपिंग. In case of a upsloping runway, there are chances that his actual glide scope would be below the ideal glide scope. So in rarest of rare cases, they adjust things as per they have a lot of experience, flying hours and all those things. Even aircraft pilots are so smart that means Air Force pilots are so smart that you at times you not even come to know that you have actually landed. Means they land on a single tire and they are very expert because they are accustomed to all type of situations. They are trained for that. Similarly, on a downsloping runway, the last image, on a downsloping runway, where there are very good chances that the actual glide scope will be higher than the ideal glide scope. Now, when you are coming higher, there are chances that you may not land at the starting point. You may land somewhere ahead of the starting point. And one accident happened around 3 years ago. You might have heard that a Mangalore flight came down. There was one flight coming from Dubai to Mangalore, and that basically overshot the runway. And Mangalore aircraft is basically a tabletop aircraft. It is on to 2 hills. So when it landed ahead, the pilots were unable to manage the speed, and finally it fell into the gorge. So we will see that video, which will give you a broader idea.
It was the breaking up of the plane as it overshot the runway at Mangalore Airport that may have saved some of its passengers. The survivors were either thrown free or managed to climb out through gaps in the fuselage as it split apart and before the flames consumed it. There was a blast, perhaps a tire bursting as the plane landed, this man says. Within 5 seconds, there was fire and smoke all over. We looked up and saw an opening and crawled through it, says this man. The flight from Dubai to Mangalore was full of Indian migrant workers and their families returning from jobs in the Gulf. More than 20 children were on board. The plane, a Boeing 737, was only 3 years old. The airport, though, has a reputation as a challenging one for pilots. Its runways are carved out of hilly jungle country and are sited on a tabletop plateau with cliff-like drop-offs. The plane appears to have skidded off the end of the runway as the pilot tried to regain control and plowed into the gorge beyond.
There are certain challenges when you approach an airport that's laid out the way this one is, and it's nothing unsafe, but you just have to really pay attention because there's not as great a margin of error there.
It's the beginning of the monsoon season in southern India, and the weather was wet, but visibility was adequate, and both pilots had experience at this airport, more than 80 landings there between them. Indian crash investigators, joined by experts from Boeing, will now try to discover why this happened. Mark Phillips.
So basically, what would have happened is that he might have landed ahead of the starting point because it was something downsloping, and then he was unable to control the speed at the last point. Since it was a gorge ahead, it went into that. Now, how HUD might help in this type of situations is that basically, since the aircraft has radars and all those things, sophisticated equipments, most important utility of HUD is during the combat and all those type of things. So, and basically, it is more useful when you have a tight cockpit type of situation. Basically, there are certain civilian aircraft. It is not a standard in civilian aircrafts. There are certain civilian aircraft which have HUDs, but it is not a standard equipment of civilian aircraft. That is why, as an spin-off, its utility is coming up in civilian also, in helicopters also. But it is not a standard equipment yet. It is a standard equipment of a fighter because there the pilot is jam fixed. He has a very fixed field of view because with this HUD, our field of view is only 25 degrees. So here, but the picture is a bit hazy, but as you can see that this circle with wings is basically the flight path symbol or the aircraft symbol. Then you have flight path acceleration system, which is basically a crocodile's mouth, greater than sign. Now, how pictorially this information, and then this is the horizon line. This is the natural horizon. This horizontal line is the natural horizon. Now, if this flight path symbol is below this natural horizon, what does this mean? It means that the aircraft is coming down or it is losing altitude. Number one. Number two, if this flight path acceleration symbol is above the flight path symbol, it indicates that the aircraft is accelerating. If it is below the flight path symbol, it indicates that the aircraft is deaccelerating. And if these two are parallel to each other, it indicates that the aircraft is gliding at a particular speed. It is not neither accelerating nor this. So pictorial information is, then you have this 490 sort of figure. This is the distance of your touch point. So in this way, you have some pictorial information which helps you to land. Now again, these are some of the utilities of HUD during takeoff. Now here you can see the center line. This is the center of the airstrip. Now, if the aircraft is going in this manner, it is pictorially visible that you are off the center. So you can adjust your thing as per your requirement. Another scenario where HUD is useful during takeoff. You know, when aircraft takes off, it takes off at a particular pitch. ऐसा तो उड़ता नहीं ना? ऐसा उड़ता है. Now there are chances that if the pitch of the aircraft goes beyond a particular degree, it is possible that the tail of the aircraft touches the ground. So in that case, this information is pitch data is available in other HUD head down displays, no issue. But in that case, HUD is able to signify a tail strike warning, which is visible at the center, that this particular takeoff may cause a tail strike, and the pilot can take decision accordingly. Either he can reduce the pitch or he can abort the flight if it is not possible at that moment. Now this is basically the automatic declutter mode, wherein this page pops up when basically the pilot is in a gimbal lock type of situation. Gimbal lock, if you read, is basically in a gyro if two axes become parallel. So if they become parallel, the third you move into the third axis and your 1 degree of freedom is lost. You're not moving into XYZ because YZ has become parallel, then you have only XY axis. So in those scenarios, there are solutions for that, and HUD gives you that visual solution for coming out of that gimbal lock type of situation. Now this is another scenario wherein on a hazy night, you can have the extreme boundaries of the airstrip. These indicators are these are the extreme boundaries of the airstrip. Now the main utility of HUD is basically during the dogfight, when two fighters are fighting. So another interesting video which you can see is that here this is basically the enemy aircraft. Now you see it is in the range of the aircraft. It is in the range. It has gone away. Now it has gone out of your range. So this all information is available to you visually at the time of fight. No doubt, entire information is coming from the sensors, and it is also available in other things. But HUD will show you pictorially in real time. Now he is following his enemy. Now he has gone out. Now there is a warning coming that he has come into low height. It become a bit hazy now. Now you see that he has finally locked the enemy, and he will shoot the yes. That is from all the sensors and other things, but it is showing pictorially. So in this way, HUD is useful during the dogfight scenario. Now these were the utilities of HUD. Now what is HUD all about? So this is a typical head-up display which we have developed for one particular aircraft. Usually there are a lot of constraints before we go for the design. We have fixed form, fixed shape, fixed space, everything is prior fixed. We have to comply with lot of lines. In aircraft parlance, there is one nose clearance line. means nothing should come in the line of the nose of the pilot. Then you have ejection clearance lines. Ejection clearance line is that when pilot in the situation of distress wants to eject, nothing should hit him. And there are FRLs and lot of, so as per design, since the HUD is at the center of the aircraft cockpit, it is situated at the central real estate of the cockpit in front of the eyes of the pilot. So it's all its dimensions are very important. It basically consists of three parts. The one at the back is the electronics block. The job of the electronics block is basically, if I tell in the simplest of the terms, is to get information from the mission computer of the aircraft and convert into a form which is suitable for the CRT which is fitted at the end of the electronics block. In simplest term, I can say this. You have certain signals, you have certain image information. Now naturally image information in analog form is nothing but XYZ. Here we have differential signals, X plus X minus, Y plus Y minus, Z plus Z minus. I have to convert them as per requirement of the CRT. I have to display it on a CRT. Secondly, what power I get from the aircraft is usually I get 28 volt DC. 28 volt DC is what is flowing in the entire. But my system needs lot of other powers. Like I need 5 volt for ICs. I need 6.3 volt for filament. I need 48 volt for video. I need plus minus 30 volt for something else, reflection amplifiers. I need certain voltages, 1.5K, 1500, 15K, 800 volt for the CRT. All those powers I have to generate from this particular 28 volt input. So I have lot of power supplies which are capable of generating those things in the space available. And I have signals which I have to convert or tune to the requirement of the CRT. This is the basic philosophy of the electronics block. However, the newer systems which we are working on, right now we don't have a display processor inbuilt into this thing. But the latest things we are working on is that we also have the inbuilt display processor. We will get the raw sensor data. Right now we are getting data from the mission computer, which is a processed data processed by a display processor which is housed inside the mission computer. But newer systems, the demand is for inbuilt display processor also. You will get the raw sensor data, you have to convert it into an image inside the electronics block, and then you have to display it. There is also demand for newer display technology because CRT is an old technology now. Why we are continuing using it is, or it is still a standard in HUD is, the reason is basically the brightness, because you have to move against the sun lot of times in case of a aircraft. Sun is at your head, sun is anywhere, there is flooding, so that brightness level which is required is not available easily with other displays. Secondly is the rapid decompression scenario. CRT is able to work to pass the rapid decompression test also, 50,000 feet to 5,000 feet in certain seconds. So that is why CRT is being continued. Then there is an optical block. Basically, the work of the optical block is to navigate the image which is being displayed onto the CRT front, plus make it collimated, so that when it comes out of the exit lens, which is something which you can see. Mouse is not working. Mouse is not working. Okay. This is basically the exit lens from where finally the light comes out. So in this optical block is basically the speciality of CSIO. Means we are the only ones who are able to design it and produce it on a lab level. Then manufacturing is basically done by one unit of Bell called Bell Machilipatnam. Bharat Electronics Machilipatnam unit is for optical units. So they basically produce it in case production comes in. And then the last part is the beam combiner assembly, which you see at the top. So ours is a dual beam combiner configuration. Now the speciality of this beam combiners is that they are so coated, thin film coating is done on these beam combiners. They are so coated that they reflect only one particular wavelength, 545 nanometer yellowish green light, which is coming out from the CRT. It is a monochrome CRT, it displays only yellowish green color, and that yellowish green color is being reflected. All other wavelengths are passed by this particular. So that is why, since this optics collimates it, it is projected onto the infinity and only one wavelength is reflected back. And that selection of that color is also very important, because yellowish green color is NVG compatible. Night vision goggles, pilot is able to see these yellowish green color only. So that is the case that that particular color is used. Now they are specifically coated to reflect, and then it is projected onto the eyes of the pilot. We are trying to develop this also as a single unit, but that needs to be holographic, and that is technically very complex. We are in the process of developing it. Instead of dual beam combiners, you need to have a single beam combiner, as I have shown in my first picture. That was basically a holographic beam combiner. So it is basically an electro-optic device which comprises of the following three modules: the electronics block, the optical block, and the beam combiner assembly. It is basically a dumb terminal which gets image from the display processor of the aircraft mission computer and displays and projects it onto the ambient of the pilot. Right now, as I told you, that we don't have an inbuilt display processor into it. However, with the
DSP processors and MATLAB processors for this.
DSP processor, we are using one for inbuilt symbology generation only. Otherwise, we are getting basically we get XYZ information. So our requirements in CRT need single-ended signals.
Yes,
So basically, we convert it into single-ended, and then other processing we do on a signal processing card, and finally V2I conversion is done through certain amplifiers, power amplifiers, and then it is displayed onto the CRT. Now, basically, the projection unit, or what we call optical block, what it does is it projects the image onto the combiner for the pilot to view. In early add-up displays, this was done using refraction, although modern arts use reflection. Projection units use cathode ray tubes, LEDs, or LCDs. In our case, we are still using cathode ray tubes. So projection unit can be below or above. Basically, in commercial ones now, what type of hertz come in is something which is loaded at the top, and it has a movable beam combiner, which can be like your sun visor. It is of that form. But in case of fighters, they are static, below, and rugged. Then combiner is basically the part of the unit located directly in front of the pilot, providing the surface onto which the information is projected for view. Combiners can be concave or flat and have a special coating that reflects the monochromatic light projected onto it from the projector unit, while allowing all other wavelengths of light to pass through. On some aircrafts, combiners are easily removable, but in our case, they are rigid. Now moving on to the electronics, this is basically a functional block diagram of the electronic circuit. I think the image is a bit small. Huh? This is basically the interconnection of HUD with the mission computer. Here you can see that you have all the signals which are required, basically XYZ signals for image. Then you have stroke raster signals for differentiation between whether it is in stroke symbology or cursive writing, or it is a raster symbology. And then you have certain synchronizations are required for communication. So those things come in, and end of slew is basically due to writing speed or working speed difference between the mission computer and the HUD to compensate those things. It is basically used. And then you have a data entry panel and rear data entry panel. These are basically to control the HUD display. Data entry panel is fitted at the front. I think I have missed it. This one is the, at the below is the data entry panel, the entry panel with switches. So by this panel, the pilot can control the display, can change navigation modes, can change display modes, because there are various auto day night modes also. The brightness of the level of brightness of the symbology can be adjusted in 3 modes. In day mode, it is full with control through a knob. In night mode, it is actually half of what is maximum in the day mode. And then we have a third mode called auto mode. So that auto mode is basically we have a brightness sensor through a pinhole out here above the optical block. That brightness sensor basically senses the ambient brightness. So we have designed an algorithm within the built-in test equipment wherein we vary the symbology brightness as per the ambient conditions. So that auto mode pilot can switch on if he does not want to change from means if there is certain case of sudden clouds and then going out, then coming in back. So in those scenarios, he has to go into dark and then suddenly he comes into bright. In those type of situations, this automatic brightness control mode is useful for the pilot. Then you have a gray coded switch for various pages. There are 16 pages which can be displayed. We have designed around 8. It can be used for future purposes. But there is the knob at the top which you can see. This particular knob is a gray coded switch, so which can be used for changing the display pages. Then there can be situations when there is some problem with the end of the aircraft. The aircraft is unable to dump the symbology, or the mission computer is unable to dump the symbology onto the head-up display. So what that type of situations, there should be some standby solution. Obviously, there should be some standby solution. Why? Because you can't, the pilot can't be left at the mercy of his approximation. So for those purposes, traditionally what was done they used to provide a graticule within the optical block. That graticule was basically something which was developed only when, which was displayed only when a particular different wavelength of light was propped up. So there used to be a valve in the optical block. When there's an emergency situation, that valve was switched on with a different wavelength, and then that graticule was visible. Graticule is something but with a glass with some incarvations on it. So that graticule was called basically static standby sight, because it gave an static idea of the angle of attack of the pilot, at what pitch angle towards downward he is. But with our system, what we provided is an inbuilt dynamic symbology, which we call it SBS, standby sight. It is an electronic standby sight. It is not a static standby sight. Since it is an electronic standby sight, it is dynamic. But again, the issue with our SBS is that if the aircraft power goes off, and if there is some problem with the input power, in that case, electronic SBS is of no use. Because naturally, if you want to run that, it is useful in the scenario when the entire aircraft is working fine, only there is symbol issues. Power, there is no issue. But if there is a power issue, then in that case, naturally, static standby sight is more useful.
So can you break for the tea break now?
Just a minute. Yes. So electronic standby site we have inbuilt. For that we have basically used a DSP processor. We have developed a design which is based on the DSP processor. And then another embedded part is built-in test equipment. That byte basically controls the entire operation of the HUD electronics, right from the startup to shutdown to two type of scenarios. One, there is some internal problem. Second, there is some external problem. If there is some internal problem, as a design philosophy, I told you at the first step, if there is any issue with any LRU, what it has to do, it should shut it down. It should shut it down itself. It should sleep. So that is one case. Second case is when aircraft does not provide you something. So in that scenario, you have to look at two things. One is the safety of the device itself, because it's a CRT based system. You might have seen a lot of screensavers in your younger ages. Nowadays they are less in prominence, but when CRT based monitors used to happen, screensaver was a must. So phosphor burning and all those type of issues we have to take care. And secondly, we have to provide something to the pilot even in those scenarios. So for that we have auto mode, we have a standby site mode, and all those things we will discuss properly after that.
Thank you. Now we'll begin. We'll have a tea break for around 15 minutes. All of you are requested to again reassemble after 15 minutes.